Welcome to SingleCrystal 5. In this tutorial, we'll show how you can calculate the orientation of your crystal from an observed electron diffraction pattern, such as this one, using the new AutoGrid command. The AutoGrid can work like magic, but we do need to set things up correctly. There are three key parameters: size, structure, and settings. Let's look at each of these in turn. Firstly, we need to be really sure of the physical size of your diffraction pattern. Secondly, we need to know the corresponding crystal structure so we can simulate diffraction in any possible orientation. Thirdly, for our simulation to be accurate, we need your instrumental settings, the wavelength and camera length of your TEM. Let's start with an observed TEM pattern, saved here as a TIFF image. I'll drag and drop this into an empty document window. Let's auto-scale this. Now we can see the pattern more clearly. And it's not the prettiest pattern because it was taken from a crystal flake and not a perfect wafer. But it's good enough to make out the reciprocal lattice geometry, which is all we need. For purposes of clarity, I'm going to colorize the pattern using the picture inspector here on the right to apply a color gradient. So let's go to the pattern coloring group and we'll click on one of the gradients and let's go down. If you hover, you get the names of the gradients: ice, heat. I'm going to go for spectrum. At this stage, the program doesn't know anything about the size of our pattern, and hence the reciprocal lattice. We only have whatever resolution was saved in the image, and in most cases this is likely to be completely wrong. We do have a scale bar, and we can use this for reference. Let's set some physical units here by clicking on the scale bar and then using the inspector that appears. Let's set our units to centimeters. We now need to use the picture inspector to specify the size of our image. We can dismiss this scale bar inspector simply by clicking anywhere on the picture, whereupon the picture inspector appears. We'll use the resolution group to specify the size of our image. Now there are three sets of text fields here representing three different ways of specifying the image size. Now in the good old days, when images were recorded on film, we could simply enter the physical size of the image in centimeters. But in this new brave world of digital detectors, it isn't always obvious what the sensor size is, as it's hidden away. Instead, we can specify either the pixel density, that's the number of picture elements per unit distance on the sensor chip, or the pixel pitch, that's the distance between the centers of each picture element on your sensor chip. These values should be well documented by your microscope manufacturer. If not, call them up and ask. Feel free to experiment with different sizes using a slider control. For example, clicking the pixel density slider allows us to adjust that in real time. Notice that our scale bar remains fixed. Now in the present case, we have the luxury of a scanned film, and so we know exactly the size of the image. And this was scanned at 1200 pixels per inch. So I can set this in the first field. Let's set the units to pixels per inch, good old-fashioned inches, and the pixel density was 1200. So let's type that in there, and I'm going to hit the return key to accept that. We now have a correctly sized observed diffraction image. And let's just auto scale that again using the magnification toolbar button, scale to fit. Let's check how well centered our image is by displaying a set of crosshairs from the tool strip. Looks like we're a bit off, so we'll auto-center the pattern on its maximum intensity. This is the 000 spot. Using our new pattern menu command, center on max intensity. There we go. We have a nicely centered pattern at the correct scale, so I'm going to hide the crosshairs. Now I have a reference structure for this material which I could load from Crystal Maker directly, or via a Crystal Maker document, a Crystal Maker text file, or a SIF. I'm going to use a SIF here. So here's my SIF, which I can drag and drop into the window. And let's just expand the window again. So this gives a simulated pattern using the current default parameters. What are they? Well, we need to replicate our observed experiment, starting by specifying the simulation type. So this was electrons, and it was TEM diffraction. If we go to our simulation inspector, we can see that we have an instrument group here, instrument TEM, and we can specify the wavelength, which was 100 kilovolts. There are some handy presets here. And then the next field we need to specify is the camera length, and this is 44 centimeters. So let's specify that. Now, camera length is sometimes misunderstood. It's actually very easy to understand. It's simply the physical distance from your sample to the detector, which is labeled L in this diagram. So if you're using some kind of crazy fudge factor like 20 meters for your camera length, you're probably not using the correct detector parameters. Why does this matter? It's always best to understand your experiment and not treat it like a black box, because that's how systematic errors happen. We can compare our two patterns, simulated and observed, to see if there's any obvious relationship. And to do this, make sure the simulated pattern is on top of the observed pattern, because the observed pattern is opaque, and if you try and display them both by holding the shift key down, the observed pattern will hide your simulated one. So you can use the sidebar and simply drag the thumbnail into position. Simulated is above the observed, and then you can shift click so that they are both now visible. Now if we zoom in, we can see that there is really no clear orientation relationship here, so that's fine. And for clarity, I'm going to hide the simulated pattern now. I'm going to command click on its thumbnail. We'll now use the grid tool to calculate the periodicity of our pattern. Simply click the grid icon in the tool strip, and the grid overlay appears, automatically sized to fit your pattern. Notice that each node of the grid has magically appeared over one of our diffraction spots. Now, if for some reason this doesn't happen, or if you've accidentally resized or misshapen your grid, you simply need to click the Auto Fit Grid button in the Grid Inspector. The Grid Inspector appears whenever the grid is active. When the picture is active, you get the Picture Inspector, click on the grid, and you get the Grid Inspector. Auto Fit Grid, and as if by magic, the grid appears nicely centered in the field of view with its nodes over your observed diffraction intensity. Notice that the grid dimensions are given in each arm, and the grid angle is shown here, the obliquity setting, as well as its bearing. We now have everything in place to determine the orientation of the crystal when this diffraction pattern was recorded. We have the crystal structure, and we have the reciprocal lattice geometry. So we'll tell SingleCrystal to use this information to calculate the orientation from us, using the auto-indexing group that's in the grid inspector. So we'll click the index pop-up and specify that our simulated pattern, KBA feldspar, should be used for indexing. And there instantly is the result. 111. What happens? SingleCrystal has calculated reciprocal lattice geometries for every possible view direction all the way out to 999, and it's found the one that best matches the observed pattern. Notice that the closest results are tabulated here in the grid inspector together with their least squares, the errors. You can see that 111 is the closest by a country mile. Let's tidy things up now by hiding the grid. We can do that by clicking this hide grid button or by using the tool strip, and we can make sure that our reflections are labeled. If we go to the labels group here, we can display all our labels if we want and set their sizes, or we can only display the most intense labels. So we now have a nicely indexed observed diffraction pattern. To summarize, when correctly set up, SingleCrystal can instantly auto-index your TEM diffraction pattern. Just remember to take a bit of time when you first use the software to understand your program's scale. And don't forget to set the correct wavelength and camera length. Auto-indexing should then be a breeze.